Similar to boiling point elevation, except that this time it's depression. So, in other words, if I were to contaminate my water, what will happen to its freezing point? From 0 degrees Celsius, it will now freeze at a lower temperature, right? So, the freezing point of the mixture minus the freezing point of the pure liquid, that's called your freezing point depression. It would be equal to negative Kf times m. Kf here is a positive number. That's called your cryoscopic constant. Cryo has to do with freezing, okay, like you've heard of cryogenics, okay. So that's freezing point depression constant, case of F, or cryoscopic constant. And m here, again, is the total molality of solid particles. Now, why is there a negative sign in front here? What do you expect T sub F compared to T sub F star is? It's freezing point depression, right? So T sub F is going to be less than T sub F star. So the freezing point of your mixture is less than the freezing point of the pure liquid. So that's going to be a negative number. That's why you have that minus sign in front there of the formula. Okay, so let's see. Here's a clicker question. On a winter day, sprinkling salt on an icy road will cause the ice to melt. B, cause any liquid water in contact with the ice to freeze. What happens when the freezing point is lowered? When you lower your freezing point, the ice will melt, right? So suddenly now the temperature is no longer, the temperature that you have is no longer the temperature where it freezes. It will freeze at a lower temperature. So that means it becomes a liquid at that temperature now. So what's the freezing point depression? Freezing point of a solution containing 18 grams glucose and 5.844 grams sodium chloride dissolved in 500 grams water. What would be the answer to this? The freezing point is equal to whatever the pure freezing point was, right? Plus delta TF. Why am I putting plus here when it's depressing? Because I know my delta TF is going to be a negative number. So when you add a negative, you get a lower freezing point. Okay, so let's calculate delta TF. How would you calculate delta TF? It's minus K sub F times molality. And in the case of water, K sub F for water is 1.86 degrees per molality. Okay, that's the cryoscopic constant for water. And this molality, you just see the previous slides, okay? See the previous question. It's the same problem we have. We have basically the same solution. 18 grams of glucose and 5.844 grams of sodium chloride. And again, don't forget that in the case of sodium chloride, you'd have to multiply the molality by 2 because you're going to get 2 particles. By the way, what if this wasn't sodium chloride? What if it was something like sodium sulfate? Instead of multiplying by 2, you'd multiply by how much? By 3, because that's going to give you 2 sodium ions and the sulfate ions. Okay? So keep in mind that you have to multiply by the Van Hoff factor for ionic compounds. Okay? So we've gone over vapor pressure lowering, boiling point elevation, freezing point depression. The last of the 4 colligative properties is osmotic pressure. What's osmotic pressure? First of all, let's define what osmosis is. Osmosis refers to the passage of solvent molecules through a semi-permeable membrane. In other words, if you have, imagine you have 2 containers here, okay? You have pure A here, pure liquid A. Let's say A is water, okay? And here you have A plus others. Okay, so A is your solvent. and most of the time we're going to be dealing with water. Now, the boundary between these two compartments, okay, we're going to make that semi-permeable membrane. By semi-permeable, we mean it allows some molecules to pass through, but prevents others from passing through. So we're going to say that this is permeable only to A, allows only A molecules to pass. Okay?